last time we were in the middle of proving this theorem by EK-LLR, which will have a long proof because it involves many new ideas and many new tools in matrix analysis. So this theorem says that you are given an undirected graph on the input tape and vertices S and T, and you have a very small work tape, logarithmic space. You have to decide whether there is a path from S to T. Okay, so basically you have to solve this problem using random bits in logarithmic space. So the way we are doing it is, till now we have seen the random walk, right? You start from S, a random walk, every neighbor you reach, there will be three, every vertex you reach, there will be three neighbors. And you will pick one randomly and then proceed. So in terms of the normalized adjacency matrix, we are basically doing matrix multiplication on the initial vector state. And the question is, how fast will this converge? So in how many steps with decent probability you will reach T? So we have made the graph D regular with D is equal to 3, and we showed that, what did we show till now? We had two lemmas. So lemma 1, right? This we showed, lemma 1 in blue, that e to the L times the initial vector, the difference of this from one, the uniform probability vector, this is exponentially dependent on the second largest eigenvalue. That was the first lemma. Second lemma we showed is that lambda is basically small, it is away from 1. Okay, it is below 1 and it is sufficiently away from 1, it is not exponentially close to 1. And this we showed using the Laplacian of the graph, right? We had this thing in blue, sigma Aij ui minus Vj square. So if we finish this proof, and now what we will do is the final lemma, where we will show that taking L to be roughly n cube log n, if you take these many steps, then with high probability you will reach T. So let L be 10 d n cube log n. Remember d is 3, right? So this is like 30 n cube. So if you take these many steps, if S and T are connected in the graph, then the probability that the random walk reaches T in nth step this is quite high, this is greater than 1 over 2n. Okay, so reaching T in the nth step is probability sufficiently high, it's 1 over 2n, and to increase the probability, success probability even more, we can boost this, we can take more steps. So let us prove this. We'll use lemma 1 and 2, proof will be easy. So let P bar be the probability vector at the nth step, so lemmas 2 and 1, they imply that L applications of A, which is the normalized adjacency matrix, on the initial vector probability vector E bar S, which is 1 at only the sth place. So, this being away from the uniform probability vector 1 bar, okay, how far can it be? So, this is dependent on how small lambda is, that we have shown is smaller than 1 minus 1 over 8 d n cube and L times that. Okay. So, it is this small. So, basically the after this L applications of the matrix, you are very close to 1 bar. The error is only this much, which is less than equal to 10 d n cube log n, which is less than e raised to minus 5 log n by 4. Right, you just use this e raised to minus t upper bound, and this is less than 1 over 2 n to the 1.5. Right, and yeah, now there is this small thing that the difference vector, we have taken the Euclidean norm, right. So, from this now you can extract information about each coordinate, how small is each coordinate. So, that you do by Cauchy-Schwarz inequality. So, you will get that a raised to L e bar s minus 1 bar, this is less than equal to, so take the one norm, okay, we want to extract information about a single coordinate. So, take the one norm, and that is related to the Euclidean norm like this. Okay, so the one norm is related to the Euclidean norm by the square root n number of coordinates basically factors. So, that is still less than 1 over 2n. Okay, so, this is the information you have about each coordinate, the sum of the magnitude of each coordinate, that is less than 1 over 2n. So, which means that if you look at the tth coordinate, right, which is the probability of reaching t, that is also smaller than 1 over 2n. Right. So, this is the difference between the tth coordinate of a to the L e bar and tth coordinate in 1 bar. 1 bar's tth coordinate is exactly 1 over n. So, the coordinate that we are interested in, this implies that the coordinate of interest, this exceeds 1 over n minus 1 over 2n, because the difference cannot be more than 1 over 2n, which is still 1 over 2n. Right. So, this means that the probability of reaching t at L step right? This probability is greater than 1 over 2n. As promised in the lemma statement, right? So this is just a simple application of what we have already shown. So basically, if you take these L many steps in the random walk, then you are almost in a random place. Okay, in the connected component of S, you are everywhere with equal probability, which means that if T was there, you are also at T. So this also means that by continuing this walk, the random walk for a longer amount, we can bring the probability above, let's say 3/4 or 2/3. So sufficiently high probability, you can reduce the error probability to quite small. So for example, if you do this calculation, so the error probability currently is 1 minus 1 over 2n, right? So if you repeat this 4n times, so this you can see is smaller than e to the minus 2, which is smaller than 1 over 4, right? So what you have deduced is L equal to, so 4n times the previous L, right? So that means 40d n4 log n, which is 120 n to the 4 log n, makes error smaller than 1/4. Okay, so error has become quite small, and if you want it further small, exponentially small, then you can go up to n to the 5. Okay, so if you take n to the 5 steps, random steps, then the error of not reaching t is exponentially small. Okay, so this is a very good procedure, and every step you can do in log space, because you only have to look at 3 neighbors. You can identify this from the input graph, and the number of steps is even if it is n to the 5, to keep track of these iterations, you only need log space. So this walk is in log space. Log space, we use this complexity class L, right? So this random walk is in log space, as we need to store the current vertex label which has only log n bits. So which means that we have shown this UST connectivity, so U path, we have shown that U path is in RL. Okay, and notice that since you are actually going to vertices, you can also keep outputting these vertices. So the whole path can be outputted as well. So also outputs the path. right? So the working space is only order log n space, and you can output bit by bit or vertex by vertex. You can write the path on the output tape. Okay, so what is next? So the next question is, can we improve on this? Okay, so this is a randomized log space. I should say this here actually. This is actually in randomized log space. So can we de-randomize this algorithm? Okay. So can we make it exactly the complexity class L? So this was an intriguing question. For 3 decades, and to solve it, several tools were developed. So one idea could be that you transform the input graph G in such a way so that your random walk converges in the fastest possible way, okay, to the vertex T. So what is the fastest possible? Well, in the algorithm we took L to be n to the 4 or n to the 5. What if you can take L to be log n? Okay, so in log n steps you are already at T. Can we achieve that? If we can achieve L log n, so logarithmically smaller L, then what will happen is we can actually explore all possible L length paths from S in log space. And this we can do because every vertex has only 3 neighbors. So you can just store which neighbor to go to 1, 2, 3 of S, and then in the next which neighbor to go to 1, 2, 3, right? So you just have to search over a L length string of 1, 2, 3. So convert G to G prime. A graph with constant spectral gap so that L equal to log n suffices. To reach any vertex from S. So basically it boils down to having the spectral gap constant, because remember lemma 1, if lambda is constant, let's say it's 1 over 10, then you just have to make 1 over 10 to the L something like 1 over n. Just reduce the error to be inverse polynomial in n. So for that L log n will suffice. So once this is achieved, then one can exhaustively look for all log n length paths from S. In log space, right, because the degree is constant. So since the degree is constant, you can actually try out all possible log n length strings in 1, 2, 3. Right, so that is how you will be able to go over all the paths. Hence, solving connectivity or undirected path question in G in L. So this is the key challenge, to convert G into this highly connected graph G prime, and these graphs are called expanders. So G prime motivates expanders. So these are highly connected graphs. So for expanders, there are many definitions that we can use, and especially the connections between the definitions are highly interesting. So we will now define it in two ways. So we will give two definitions. So first is the algebraic definition. So we call a graph G and n d lambda expander if G is n vertex, d regular, d is the degree, and the second eigenvalue of G, which is lambda G, this is smaller than lambda. Okay, so the spectral gap is bigger than 1 minus lambda. That's the point. So you want lambda to be small. The smaller lambda is, the better algebraic expander G is. And instead of looking at only one graph, we will obviously, or we will be more interested in actually graphs that are growing. Okay, so a family of infinite graphs. So a d comma lambda expander family so graphs Gn, infinitely many graphs. This is such that for all n, Gn is n d lambda expander. So you can take d to be 3, and in general you can ask the question, so there are two parameters in expander family, right, d and lambda. So for a given d, you can ask how does lambda behave as a function of d. Okay, can you make lambda extremely close to 0, or is there a limit? Is it away from 0? Is it large in terms of d? So actually it depends on d pretty strongly. So there is this result by Alon and Bopana. They showed that lambda G is greater than equal to roughly 2 over square root d. So if you take d to be 3, then this is 2 square root 2 by 3. So yeah, you cannot make the second largest eigenvalue arbitrarily small. It will really depend on the degree d parameter, and this expression is a bit more non-trivial to show, but as an exercise you can show that lambda g is greater than 1 over square root d by using trace of a square. So that's a hint. You can actually show in a much easier way that lambda is at least 1 over square root d, but Allen-Bopana bound is better and it's optimal. Okay, it is saying that actually it is more than 2 over square root d, almost. So graphs with lambda equal to 2 square root d minus 1 by d, these are called Ramanujan graphs. And their explicit constructions are known. So that result is due to Lubotsky, Phillips, and Sarnak. Okay, so these objects are very important. They are heavily studied, and using analytic number theory, there are these constructions due to LPS of Ramanujan graphs. Okay, so the degree there is actually prime power plus 1. So it's not for every degree, but for these prime power plus 1 degrees, these constructions are known, and they achieve this Allen-Bopana bound. So this is an optimal bound. Point being that these infinite families are constructible. Okay, they not only exist, but they are constructible, and we very well understand the spectral gap. So this is some advanced topic independently. We will not go deeper in this. Instead, what we will do next is define expanders combinatorially. So the combinatorial definition of an expander is we'll call these now, instead of expander, we'll use the term edge expander. So ND rho is an edge expander. If G is an n vertex, D regular, graph such that this will be more pictorial than the algebraic definition. Right? In the algebraic definition, it was not clear why you pick the second largest eigenvalue, unless you recall lemma 1 that we had shown, where if lambda is smaller, then the convergence is faster of the random walk. But combinatorial definition will be even simpler and more directly related to connectivity. So here what we will say is that if you take any subset in the graph, then there are many edges going out. So if G is an vertex deregular graph such that for any subset of vertices, of size small, let's say smaller than n by 2. So say you take you take half the vertices as S, then count how many edges are going out. Right? That's the connectivity information, or a way to measure connectedness in the graph. So the edges that are going out of S to S complement is large. So this E S comma S bar is basically these edges going from S to S bar. This is all undirected edges. And D times S, you can think of this as the max that could happen, right? Because there are S vertices, so and the degree is D, so there cannot be more than ds edges going out. And rho is the fraction that the parameter given to you for edge expansion. So larger rho is, let's say rho is 1, then you are actually saying that maximum possible edges are going out of S for any S. And if rho is, let's say 0.99, then still many edges are going out. Okay, so this is a very good level of connectivity inside the graph. So in the algebraic definition, we want lambda to be small. So close to 2 over square root d. While in the combinatorial definition, we want rho to be large. So how large can it be? Can it be 1? You can show that it cannot be 1. So the maximum it can be is actually half. Okay, because you want it to be true for every subset. So if you want it to be true for every subset of size n by 2 or less, then you can only afford half. So that's what we want optimally. So why half? This you can think about. And now what we will do is, so next we show their equivalence. So why are these two very different definitions of expansion why are they equivalent, right? This is not at all clear, although intuitively we have some feeling. So the combinatorial one is the natural meaning of well connectedness, and the algebraic one comes from lemma 1, because lemma 1 says that the convergence of the random walk will be rapid, or if lambda is small. But say, what is the quantitative relationship between that lambda parameter and this rho parameter? So here it is. So first we will show G, if G is an ND lambda expander, so algebraic definition, then G is also an ND 1 minus lambda by 2 edge expander. Okay, so if G satisfies the algebraic expansion definition, then G also satisfies edge expansion definition. So lambda you want to be close to 0, and you can see in the implication that then edge expansion will be close to half. And theorem 2 is the converse. So G is an ND rho edge expander, then G is an ND. So what can you say about the second largest eigenvalue of edge expanders, right? That is the question. So it will not quite be the converse of theorem 1, it will be slightly weaker. What you will get is 1 minus rho square by 8. So again you can check if rho is half, which is the best edge expansion possible, then in the bound for second largest eigenvalue or for the spectral gap, what you are getting is 1 over 32. That's the relationship. So this anomaly that it's not if and only if, so we have to write actually two theorems instead of just one theorem with if and only if. This is we can also state it as Chiger's inequality. So basically it tells you what rho is for a graph in terms of the lambda parameter, the second largest eigenvalue. So the edge expansion of a graph, any graph, will be at least 1 minus lambda g by 2. So there is this gap that you get for edge expansion. So if in the best possible case lambda will be 0, I mean ideally speaking it could be 0, so then this is telling you that rho is between half and square root 2. Okay, that's a wide range. So the point is that this is not precisely telling you what rho is, but it is giving you a decent lower bound on the edge expansion. Okay, so as you keep making lambda smaller, edge expansion improves. So it matches our intuition. So this is a way to, you can think of Chiger's inequality as a way to measure bottlenecks in a graph. So let us, yeah, that's only the inequality which kind of connects both theorem, combines theorem 1 and 2. But we have to prove these theorems individually. Proofs will be sort of related, but still they will look different. So let us start with the proof of theorem 1. Okay, we have to connect this algebraic structure with the, or concept with combinatorial concept. So the number of edges that go out of S we want to estimate that, right? So you are assuming that G is a given d lambda expander, So the second largest eigenvalue is smaller than lambda in magnitude. From this you want to deduce that if I take a subset S in the graph, how many edges are going out? So for that actually we will consider a function. It is called the Laplacian quadratic form. It will measure this exact thing. Its evaluation will measure how many edges go out of S. So the number of edges going out of S are estimated by considering this Z quadratic form, which is Aij times xi minus xj square, and Aij is the adjacency matrix. Okay, so just go over all the vertices. So yeah, this seems like a weird function, but it has a name. It appears in many places. It is called, and we have actually used something like this also before, when we wanted to use the connectedness of a graph to deduce that the second largest eigenvalue is sufficiently away from 1. Okay, there also we used something of this type. So this is, in particular, this is called Laplacian quadratic form. Now you have to realize that this could measure number of edges that go out of S. How? So basically the vertices which are in S, when I is in S, you give them value 1, and the vertices which are not in S, you give them value 0. Okay, so then this difference squared, this is 1 only when you are looking at an edge that crosses. Within S and within S bar, it is 0. Okay, so let us formalize this. This is the bridge between algebra and combinatorics. So define vector x bar as, so the ith coordinate is S bar if I is in S, and it's minus S otherwise. Okay, so that's the definition of xi for all I1 to n. So now you can see the value of z at x bar. So let us break the sum into 3 parts. So one is within S, then within S bar, and then across. That's the rest. So what are these 3 parts? So as I said, this xi minus xj square, right? For I in S, it's 0. I and j both in S, it's 0. I and j both in S bar, it's 0. And now let us see the last thing. So this will be, I mean, S to S bar is or s bar to s, it is the same thing. So, there is a factor of 2, and what is the sum? So, you are looking at aij xi minus xj square ij in, let us say, s to s bar, right. So, you can notice that x minus xj is actually s bar plus s, which is n. So, this is just n square. So, you get this equal to 2n square times sigma aij. Which is equal to, so sigma aij is it is the normalized agency matrix, right. So, it is either 1 by d or 0 every entry. So, you will get in particular 2n square by d factor, and how many will be 1? Well, that is exactly the number of edges going out. Right. So, this is what this Laplacian evaluates to, and so this is one way to evaluate the Laplacian, and next what we will do is we will do this calculation in a different way. Okay, we will relate this to lambda, the second biggest eigenvalue. So, we have this Laplacian quadratic form Z, and we have shown that value at x bar is giving you essentially the number of crossing edges. Let us now recalculate it in a different way, so that this connectivity information relates to the eigenvalue. So, you can expand Z as just square, expand the square, right. So, you will get xi square minus 2 xi xj and xj square. Which is equal to, so sigma I outside, sigma aij j here, minus 2. So, now the nice thing is that this aij xi xj term, this you can see as the action of A on x bar. E x bar and then inner product with x bar. So, that is the nice thing about this calculation, and hence this expression of Z. And the last thing is symmetric to the first one. Okay, so now clearly this this calculation we have done before, that sigma aij over all j, this is just the ith row sum, which is 1. So, you will get norm of x bar square minus plus again norm of x square, and furthermore you know something about ax bar. So, note that here x bar that we have chosen, it satisfies this property. So x bar is actually orthogonal to 1, right? Because if you add it up, sigma xi, what do you get? Size of s times s bar minus size of s bar times size of s, which is 0, right? So that is a very useful thing in the second green calculation, because you know that on such vectors the action of A scales by at most lambda factor, right? So Ax bar is less than equal to norm of Ax is at most the norm of x times lambda. So what we can write is, this is greater than equal to two lambda times x bar square. So what we are using here is these two things, that Ax bar's norm is bounded by lambda times x bar norm, and then you also use that the value of inner product this is less than equal to the product of the lengths. Right. So the first thing, Ax bar is less than equal to lambda x bar. There you are using that x bar is orthogonal to 1, and lambda is the second largest eigenvalue in magnitude of A. So by the properties we have seen before, this is true. And second is simply saying that inner product is bounded by the product of the vectors, length of the vectors, right? This is clear by geometry, because we are working in the real Euclidean space. So that gives you a nice relationship of a lower bound on Z. So this means that Z is at least 2 times x bar square times 1 minus lambda, and it is exactly number of crossing edges. Right. So that gives you a relationship. So what is this equal to? So this is equal to 2 1 minus lambda times what is sigma xi square, right? So sigma xi square is s times s bar square plus s bar times s square, which implies that the number of edges, crossing edges, is at least d over 2n square times 2 1 minus lambda times, so bring ss bar outside, and you are left with s plus s bar, which is n. So that is 1 minus lambda d by n times ss bar. S you have assumed is less than or equal to n by 2 in size. So this is greater than or equal to S bar is then S bar is then at least n by 2 in size, right. So, that n by 2 times S. So, that is what you get. Let us write it like this. Okay, so 1 minus lambda by 2 times d times S. So, this in particular tells you that rho is at least 1 minus lambda by 2. And G is an n d 1 minus lambda by 2 edge expander. Okay. And this we were able to achieve because of this bridge between algebra and combinatorics, which is the Laplacian quadratic form. So, we actually evaluated it at 1 x bar, and we evaluated it at, well, we evaluated at 1 x bar. So, that gave us the first equality, z equal to basically number of crossing edges, and then we did a different calculation on z to get a lower bound, which turns out to be 1 minus lambda. Okay, so, that is a brilliant connection. So, we are 50% done. Next we will do the converse of this, almost converse, proof of theorem 2. So, now assume G to be an ND row edge expander. And given this combinatorial property, now we want to study how we want to estimate the second largest eigenvalue of the graph. So, again we will use this bridge called Z. So, we again estimate Z. But we evaluate is estimated at a different evaluate at a different x bar. Okay, now x bar will actually be an eigenvector. So, use x bar equal to an eigenvector. Of lambda 2. Okay, so, the second largest eigenvalue of the matrix, pick an eigenvector x bar, and now estimate Z afresh. So, what you have is A times u bar is equal to lambda 2 times u bar, and you have that eigenvector u bar is orthogonal to 1. So, in fact, let us take this as a definition. So, pick a non-zero u bar such that this happens. So, this means that u bar has positive and negative coordinates. So, let us collect them. In V bar and W bar respectively. Okay, so what we have is we have basically written u bar as v bar plus w bar with both v bar and minus w bar. Every coordinate is non-negative. Okay, so we have separated into positive locations, negative locations. So based on this, now we will estimate z next time in the next class.